Okay, section 3.2, digital signals. I'm Dr. Piccone. Garbini and Devine are my co-authors on Real-Time Computing for Mechanical Engineers, our book with MIT Press. Check it out on their website or the companion website, rtcbook.org. Digital signals. A signal is a time-varying quantity that represents encoded information. We are concerned with electrical signals, which have time-varying voltage and current. An analog signal represents continuous valued quantities, e.g. real numbers, while a digital signal represents discontinuous valued quantities, e.g. integers, called discrete quantities, which are typically finite in number. Note, however, that digital signals still have values at each moment of time. It is just that they represent a discrete value. Many digital signals represent just two discrete values, and often, but not always, this is implied in the use of the term. We will implicitly use digital to signify two-valued signals unless otherwise stated. The two-valued binary numeral system is a common way to model digital signals. This is closely tied to the bits stored in computer memory and operated on by a processor. In fact, it is common to talk about a digital signal carrying bits from some node to another at a bit rate, which are abstract ways of considering the function of a digital signal. Okay, quick introduction to digital logic families. Digital devices that carry digital signals, are produced by many different manufacturers. And for these devices to be compatible, they must agree on signal characteristics such as voltage level and impedance. The specification of these characteristics constitute a logic family. A logic level of a logic family is the nominal value that represents either logical true, 1, or false, 0. A collection of logic families called transistor-transistor logic, TTL, used to be very common, but it is now primarily used by scientific instruments for clock and trigger signals. TTL requires a 5-volt supply and has output and input logic levels as shown in the figure. So in the figure, we have on the left-hand side output ranges in volts, where 1 is represented by 5 volts down to 2.4 volts, whereas 0 is represented in the output by 0 to 0.4 volts, and forbidden are the voltages between 0.4 and 2.4 volts on the transmission side or the output side of the channel. On the other side, once we've gone through the channel, we should have on the input, for an input device, we should have 1 represented by 5 volts down to 2 volts. Notice that the range got a little bit bigger. And 0 to 0.8 volts for representing 0. That also got bigger. These larger ranges on the input side are there to allow for some distortion and noise in the signal that was transmitted. This difference between these ranges is sometimes called noise immunity or noise margin. Although TTL is deprecated for new devices, the TTL logic level, nominally 5 volts, remains common, so you'll still see that. The most common logic families in modern computers are complementary metal oxide semiconductor, or CMOS for short. The CMOS logic levels depend on the supply voltage, VDD, which can be constant, close to 1 volt, up to around 18 volts. But the most common values are 5, 3.3, and 2.4 volts. Typical levels for VDD equal 3.3 volts are 3.3 volts for logical true and 0 volts for logical false. However, a range of values around each of the typical low and high levels is permitted. TTL and the various CMOS logic families are mostly incompatible with each other. However, there are integrated circuits available for converting among them when necessary. Okay, so that's a little introduction to digital signals and digital logic families. We'll see you in section 3.3.